The objective here is to describe what the Intel manual says about QNaN floating point indefinites, and we're going to go into the half precision floating point operations section. We're on page 103 here, and let me go ahead and apologize from the beginning because we're going to take two field trips, one to Stack Overflow and another one to Wikipedia, just because these sections are really small and I feel really guilty making a very tiny video. So maybe I'll get through the manual part first, and then we're going to jump over into those other sites at the end. So if you wanted to skip it, that's totally understandable. And before I begin any reading, it might do you good to answer these questions. What does a Q stand for in a QNaN? And what is its opposite? We'll put opposite in quotation marks. And also one more review to begin question, what are QNaNs even good for? So here we go, starting with QNaN floating point indefinites. For the floating point data type encodings, it looks like there's three of them. You got your single precision, double precision, and double extended precision. Of those three, one unique encoding, a QNaN, is reserved for representing the special value QNaN floating point indefinite. So what is indefinite? That is something without limits. Or at least according to wikidiff.com, where it says that an indeterminate is not accurately determined or determinable, while indefinite is without limit. So the x87 FPU and the streaming SIMD extensions, all four of them, and the AVX extensions, they return these indefinite values as responses to some masked floating point exceptions. And table 4-3 shows the encoding used for the QNaN floating point indefinite. So let's scroll up to 4-3 real quick. So we went from page 103 all the way down to 92, and here it is, the QNaN floating point indefinite. They should have done that freezing the top row thing that I know you can do in Excel or Microsoft Access. But the top row, we got the sign bit, the biased exponent part, and then the significant part. So for a floating point indefinite, you got your sign bit set to 1. Here's the bias. This is your fraction part. And for you visual learners here, I just went down to the single precision part, so just to represent a QNaN floating point indefinite in single precision. So there's the question, how do you represent the QNaN indefinite? Again, single precision, 32 bits. So we got our sign bit set to 1, as if this was a negative number, but we know that it's an indefinite. The next 8 bits are all 1s. Then we have a 1 for the integer, so normally this would be like 1 point, and then here's the Montesa section. It's also called the significand, and also known as the fraction, which includes that integer or j bit right there. Still pretty sure the j bit is implied, it's not even there at the hardware level. Well, there you have it, table 4-3 showing the encoding for that floating point indefinite, and I just called this like a very special kind of QNaN, the indefinite one. And I'm just saying that as opposed to this other one right here that almost looks the same, but you got a couple X's there, meaning it can be on or off, set or clear. Oh yeah, and there you go, look in the notes. Integer bit is implied and not stored for single precision and double precision formats. And now I'm asking, what about that third encoding? What was the third encoding called? Double extended precision? So there's the question. Are integer bits stored in double extended precision floating points? Make sure you're not confused and think of this as frames per second. It's a different tech concept. Well, let's add another encoding to our three floating point encodings, and this is called half precision floating point. And these values are not used by the processor directly for arithmetic operations. Two instructions, and there they are, provide conversions only between half precision and single precision floating point values. Now, the SIMD floating point exception behavior of those two instructions are described in section 14.4.1. We'll get to that eventually. And after reading that sentence, I kind of thought, like, is half precision just a SIMD thing? Well, you can see we only got 4 questions, and I just need more, so we're going to go ahead and let's go to Stack Overflow first, just to hammer away at this indefinite concept right there, and then we'll go ahead and answer my question right here about half precision and kind of read through the wiki to better understand that. So here we are on good old Stack Overflow, and somebody asked the question, what is the difference between end, as in indeterminate, and NaN numbers? And this person is coming from a C++ perspective, but I just wanted to share this particular post because I had learned more about NaNs by reading it. And I know we're a little off in our research because I wanted to learn more about indefinite, but here we are with indeterminate. And if you look through the results, basically they all seem to say the same thing, that indefinite is without end. But I just have such a problem with that because isn't that what an infinity number is? In a variety of other contexts, though, you'll see that there are indefinite prison sentences. There is an indeterminate tomatoes. I don't know. But let's go back to that Stack Overflow question, and let me share with you this part. So they say, what is the difference between these two? They are both the same thing. Some platforms choose to display a non-number as some variant of a NaN. Okay, so variants, I assume SNAN and QNaN. And then they say other platforms are choosing to display it as a variant of an indeterminate. And there's that C++ code for you. Well, I like this person. They say apparently they are not the same per se. On Microsoft, IND appears to be a special case for NaN. Specifically for IND, the exponent part is all ones. And the Montesa has a 4 in it. Of course, this is hexadecimal, so convert that to better see that floating point image in your mind, bit image that is. But we can check this sentence, any other non-zero Montesa gives us a NaN. We could check that with our knowledge here. Go back to page 91. They said any non-zero is a NaN, so here's our NaNs, and here's the significand. And look, they're correct, because there are ones here. It's not all zeros. And I sure wish they just didn't call the same concept 3 different things, you know, fraction, Montesa, and significand. But what I like about this part is the person is giving us some like solid examples, even though they may be wrong. And let's read it and I'll take you to the comment that calls them out. Where they say that some mathematical operations don't make sense, such as square root of a negative number. Both square root of -1 and a logarithm of -1 would return a NaN. Okay, so that makes sense. They say Windows displays a NaN as -1 indeterminate or indefinite, while Linux displays just NaN. Now, other operations that would return a NaN, these include 0 divided by 0, 0 times infinity, and infinity divided by infinity. I wonder what the Unicode for that infinity sign is. Well, in the comments, a person does say it's not a Windows versus Linux thing. It's a compiler standard library that dictates how NaN should be shown. So I thought that was really insightful. And then the Sombrero kid here says that some operations don't make mathematical sense as like an incorrect sentence. They do, but the results just can't be stored in a floating point number. And they go on to say, since we're talking about real numbers earlier, that a square root of -1 is I, and an imaginary number is I. That just can't be stored as a float. So I don't know how helpful that was to you guys. I just think the compiler part was especially helpful. So helpful, in fact, we should turn a question into it. So what determines how NaNs are shown? The answer would be the compiler determines that. Another good question could be, what is an example of an imaginary number? Since we spent so much time talking about real numbers, that'll be a helpful dichotomy to create in your mind. And another question, what is the difference between indeterminate and indefinite? Maybe I should call this the like difference video or the dichotomy video, because we're just going with opposites a lot. Well, I just want to get through a few paragraphs here about half precision. In computing, half precision is a binary floating point computer number format that occupies 16 bits. Okay, that makes sense. 16 is half of single precision, so half of 32 bits. Going with that standard, the 16-bit base 2 format is referred to as binary 16. I hadn't seen that before, so that's good to know. It is intended for storage of floating point values in applications where higher precision is not essential, so they're used when precision does not matter. So simply asking, when are half precision floats used? And what I like about this Wikipedia article is it's about to give us some hardcore examples so we can connect that in our minds with Intel's mention of the half precision floating point format. So higher precision, not essential. It's not essential for performing arithmetic computations, although implementations of this IEEE standard are relatively new. Several earlier 16-bit floating point formats have existed, including that of Hitachi's HD 61810 DSP, which was from 1982, I guess. And then you got this thing, but I want to point out the Voodoo graphics processor. So alright, we're in the graphics realm. Well, NVIDIA and Microsoft defined the half data type in the CG language, which apparently is a high-level shading language. Never heard of a shading language before. But using context clues, it says Microsoft is using this for programming vertex and pixel shaders. Well, it released in 2002, so they are not kidding when they say this is like a relatively new thing. Now, it's been implemented in silicon in the GeForce FX, which is also 2002. ILM was searching for an image format that could handle a wide dynamic range, but without the hard drive and memory cost of floating point representations that commonly used for floating point computation. But just to finish this video up, they say that this format is used in several computer graphics environments, including all of these as examples. The advantage over 8-bit or 16-bit binary integers is that the increased dynamic range allows for more detail to be preserved in highlights and shadows for images. And the advantage over 32-bit precision, single precision binary formats is that it requires half the storage and bandwidth at the expense of precision and range. So I ask, why is the half precision format useful? And the answer is simply, you can use it to create more detail in the highlights and shadows of images, all the while saving in storage and bandwidth. And let us truly finish this video by mentioning that the F16C extension allows x86 processors to convert half precision floats to and from single precision floats. That brings us right back home. Right here, these two instructions provide conversion only between half precision and single precision. So I hope this helps you wrap your mind around this whole QNaN indefinite thing. It's just one short paragraph here on page 103, and then another 2 sentences about half precision. Then the Intel manual just keeps it going and talks about rounding, which is really interesting, and we'll cover that in the next video.